we just saw the definition of a cycle, which was a special kind of permutation. Just to remind you, if you had a permutation cycle like this, then that meant the permutation which sent 1 to 2, and 2 to 3, and then 3 back to 1 again, and left any other numbers alone. Now, unfortunately, not every permutation is a cycle. So let's look at this example here, where S is the permutation whose 2-row notation looks like this. So this is an element of S4. Now, I claim that this thing S is not a cycle, and to see that, let's draw some diagrams. So here is the number 1, and what S does to 1 is S sends 1 to 2. So I'm going to draw an arrow like this to tell me that S sends 1 to 2. Then if you look at the second column of the 2-row notation, S sends 2 to 1. So we go around like this, and we do have a cycle there, but if we look at what happens to 3, 3 is sent to 4, and then 4 is sent back to 3. So while S is not a cycle, what you can check is that actually S is equal to the 2 cycle 1, 2 composed with the 2 cycle 3, 4. So S is not a cycle, but it is the product or composition of 2 disjoint cycles. And this is not a coincidence. So in fact, every permutation belonging to a symmetric group Sn is equal to a product of disjoint cycles. Remember, product means composition. We use this multiplicative language to talk about composing permutations. I'm not going to give a full proof of this theorem. If you'd like to see one, you can look it up in the notes for Math 5. What I will do is try and give you a very different explanation to the one that you'll find in the notes, which shows you why this ought to be true. And the explanation is going to be not really a formal proof, but I'm going to draw a picture, and I'm going to discuss why my picture looks the way it does. So we're going to draw a bunch of blue dots like this, and these dots represent the numbers 1 up to n. So n is pretty large here, and each of these dots represents one of the numbers 1 up to n. And I'm going to draw a diagram where for each number I between 1 or n, I'm going to draw, so I is represented by one of my blue dots, and I'll draw an arrow from I to S of I. So S is the permutation which we want to express as a product of disjoint cycles. And then I'm going to keep going, so I'll draw a line from S of I to S of I. And then I'll draw a line from S of I to S of I. And so on. So we're just going to keep going and going and going. So let's say we do this. We pick any number between 1 and n to start with, and we draw this arrow, and perhaps it looks like this. That's the first step. So I drew a line from some number to S of that number, and then I'll do it again, and I end up somewhere else. Okay, and I keep going, and I keep going and going and going. And now, eventually, if I do this n plus 1 times, for example, I can't just keep getting a new number forever. Eventually, I must revisit one of the blue dots that I've already visited. So we can't keep getting to a new point forever. So a question for you, which you should pause the video and think about, is could it be that something like this happened, that we ended up going back to a point we've revisited in this manner? Okay, and the answer to that is no, that can't happen. And the reason that can't happen is that S is supposed to be a permutation. A permutation is a bijection. In particular, the permutation is 1 to 1. So we can't have a diagram like this, because if that were the case, S would send both this thing and this thing to here. It can't do this because it's 1 to 1. So we can't be in this situation. Okay, but my argument that S had to repeat itself was still good. So in what way can it repeat itself? Well, the only way it can repeat itself is if the first time we revisit a number is when we get back to the start, to the blue dot that we started off with. In other words, we have to go round in a cycle like this. And if you then consider, well, okay, let's pick another number and draw some arrows to see what s does to this number. So let's pick this number here. Let's say it went here and then here. And again, eventually I must come to a blue dot, which I've already seen before, because there's only a finite number of blue dots, so eventually it's got to happen. Now, could it be that this happens? Again, pause the video, answer the question yourself. Okay, the answer is this can't happen for exactly the same reason as before. S is supposed to be 1 to 1, and so it cannot send two different blue dots to this blue dot. Can't send this blue dot and this blue dot to the one in the middle. So, first of all, my new trail of arrows can't intersect the old trail of arrows. And second of all, when my new trail of arrows repeats, it must repeat by going back to the start, like this. Okay, so we can just keep this argument going. So perhaps we start again here. Maybe this thing gets sent to itself. So we could draw an arrow like this. And if we do another one, maybe this goes to here, and this one goes to here, and this goes to here, like this. You can see what we're getting here is a bunch of disjoint cycles, and this is the reason that every permutation is expressible as a product of disjoint cycles. So what if we actually wanted to do this? Like we were given a permutation, perhaps in two-row notation, and we wanted to find an expression for that permutation as a product, a composition of disjoint cycles. That's what is meant by a disjoint cycle decomposition. So a disjoint cycle decomposition means an expression for a particular permutation as a composition, as a product of disjoint cycles. So the method we can do this is by following what I was doing drawing my diagram on the last slide. You start off by picking a number which is not yet in one of your cycles. Then you compute the image of this. So if your permutation is called S, I mean you compute S of the thing you started off with, and then S of that, and then S of that, and then S of that, and you keep going until you go round in a cycle. And when you've got back to where you started, you've got your cycle, so you write that down. And then finally, if all of the elements belong to one of your cycles, then you're finished. You can stop. Otherwise, you should go back to step one and pick another number which doesn't appear in a cycle. Okay, let's do this in an example, because when you see it working, you'll see this is really simple to do. So I've got just here a permutation S given in two-row notation, and I'm going to compute an expression, a product of disjoint cycles equal to S. So how do we do it? The step one tells us to pick a number which isn't yet in a cycle. So I may as well choose number 1. It doesn't matter what I choose, but I'll choose number 1. And you can see that what happens is S sends 1 to 4. So I should put 4 as the next number in my cycle. Okay, what happens to 4? S sends 4 to 3, so 3 must be the next number in my cycle. S sends 3 to 9, so 9 must be the next number in my cycle. It sends 9 to 6, so 6 must be the next number in my cycle. And finally it sends 6 back to 1. So 1 is already in my cycle. I must have got to the end of my cycle, so I need to close off the cycle here. 6 went back to 1. So that's our first cycle. And we now have to answer the question, are there any, we're on step 3, are there any elements from 1 up to n which don't belong to my cycle? Yeah, for example, 2 is not in there. So let's start our next cycle. I'll do this in a different color. And we pick a number which doesn't belong to one of the cycles yet. So 2 doesn't belong to our cycle. So S sends 2 to 7. So 7 should be the next thing in the cycle. It sends 7 to 5. So that's the next thing. And it sends 5 back to 2. So my cycle must close here so that 5 goes back to 2. Okay, now we're at step 3. Are there any elements between 1 and 9 in this case which are not in any of our cycles? Well, the answer is yes, there's no 8. So let's look what happens now. We have to start a cycle with 8. Then we look what S does to 8. S sends 8 to 8. Okay, so the cycle stops straight away. All right, so we've now found our disjoint cycle decomposition. All of the numbers 1 up to 9 appear in one of those cycles. So we stop. We've found our disjoint cycle decompositions. But I want to make a comment about this, which is about this one cycle that appeared at the end. So any one cycle is actually the identity permutation. Because if you think what a one cycle does, so this one cycle which just contains the number 8, for example, well, it sends 8 back to 8, so it sends 8 to itself, and it sends every other number that doesn't belong to that one cycle to itself as well. So it sends every number to itself. In other words, it is the identity permutation. So for that reason, we often omit one cycles from our disjoint cycle decompositions. And it's fine to omit them, because if they're equal to the identity permutation, then composing with the identity doesn't do anything. So it will be equally okay to write this as 1, 4, 3, 9, 6 composed with 2, 7, 5. And often, but not always, we will miss off one cycles because they're just the identity permutation. Okay, let's do another example where we're going to compose two permutations. So we've got these two permutations, two cycles which are not disjoint, and we're going to try and express this as a product of disjoint cycles. So the game that we're playing, the task that we're setting ourselves, is to express this permutation as a product of disjoint cycles. Right? It's certainly a product of cycles as it is, but it's not a product of disjoint cycles, because, for example, 4 belongs to both of those cycles, so they're not disjoint. So let's recall what this notation means, right? Those two cycles that I've written there, those are permutations, they're functions. So this is a function composition. This is the cycle 1482 composed with the cycle 349851. So that is the new permutation, whose rule is that you first do this permutation, and then you do this permutation. All right, so let's just follow the procedure that we've already seen for how to come up with a product of disjoint cycles expressing a particular permutation. So the idea was that you began with any old number you like, and then you look what happens to it under your permutation. So if we start with the number 1, then the first thing we have to do in our composition is we apply the cycle on the right, so 349851. So that sends 1 to 3, and then the second cycle sends 3 to itself, because 3 doesn't belong to that cycle. So let's actually write this as clearly as we can. Let's give some names to these cycles. So we'll let S be the first cycle, 1482, and we'll let T be the second cycle, 349851. And then the permutation we're dealing with is S composed with T. So if we want to know what S composed with T does to 1, S of T of 1 is S of 3, which is 3. So our cycle should start 1, 3. Now we need to think what happens to 3. So S of T of 3 is S of 4. So you can see that T sends 3 to 4 just here. And S sends 4 to 8. So S composed with T sent 3 to 8. So that's the next thing in our cycle. Okay, let's keep going. So what happens to 8? So the cycle on the right, T sends 8 to 5, and then S sends 5 to 5. So we get a 5. Okay, what does T do to 5? 5 goes to 1, and then S sends 1 to 4. Okay, what happens to 4? 4 goes to 9 on the permutation on the right, and then the permutation on the left, S sends 9 to itself. Okay, T sends 9 to 8, and then 8 goes to 2. And 2, so T sends 2 to 2, and then S sends 2 to 1. So we've actually finished the cycle here. 2 must go back to 1, so we close the cycle there. And then we have to decide, are there any numbers which don't belong to this cycle? So if we were talking about permutations in S9, then we look for all those numbers. 1 is in there, 2 is in there, 3, 4, 5 is in there, but 6 and 7 are not in there. So if we want to include all the 1 cycles, 6 should be in a cycle on its own, and 7 should be in a cycle on its own, because both of those permutations, S and T, send 6 to 6, and both of them send 7 to 7. So this will be equal to this, and of course if we wanted, we could omit those 1 cycles since they're both equal to the identity. So there is a product of just 1 disjoint cycle, or 3 if you include the 1 cycles, equal to this composition of 2 non-disjoint cycles.